Good morning. This is Ms. Billerbeck, and we're going to talk about rational exponents and properties of exponents. So first, let's talk about what are rational numbers. So rational numbers are the set of real numbers that include integers. So -3 is an integer. Counting numbers, 0, which is a whole number. Fractions, any number that can be written as a fraction is rational, and terminating decimals, that means decimals that end, so 0.81, or repeating decimals, 0.123, that would be a rational number because it's a repeating decimal. Now, things like pi, which never end, that would be irrational. Okay? So let's look at what we know so far. So we know that 3 squared means 3 times itself twice. So 3 squared equals 3 times 3, which equals 9. So what is 3 1/2 then? That's 3 with a rational exponent of 1/2. What could that be? So let's take a look at what we do know. Okay, so what we've learned before are basic exponential properties. So we've learned the product of powers. So product means multiplying. So this is a power, a to the m is a power, times another power, a to the n, equals a to the m plus n. So the product of powers follows this rule. Quotient of powers, so I have a to the m divided by a to the n, which equals a to the m minus n. Then we have the power of a power. So I have a power in here, a to the n, m as in Mary, and then it's n as in Nancy up here. So a to the m, n. So that's a to the m times n. Now this one and this one get mixed up quite a bit. So what I have determined is a good way to look at it is this has one base and 2 exponents. So we multiply. This one has one base with an exponent and another base with an exponent, so we add. Our next rule is the power of a product. So if I have the product a times b in parentheses and m, so a times b to the m, then I can distribute this m to both of these terms. So a to the m, b to the m. These are actually bases, so I'm going to distribute that to this base and to that base. So a to the m, b to the m. Okay, so other properties, if I have a to the negative m, that's just going to be 1 over a to the m. So if you think about it, when you don't want to be someplace, your attitude gets a little negative. So the negative is a location thing. This base A is not happy about being there, and it wants to be on the other side of the fraction bar. Okay, so that's when we use a negative to move the base to another side of a fraction bar. So if we wanted to move this up to this part of the fraction, we would just make that a negative m, which would be a to the negative m. Now a to the 0 equals 1. Now my other class did want me to go and prove that, so why does a to the 0 equal 1? So let's take a look at that. For anyone who might miss this lecture. So if we have 125, 125 equals 5 cubed. 5 times 5 times 5. Now, if we take 125 and we divide it by 5, that equals 25, but it also equals 1 less 5 multiplying, so that's 5 squared. Now, if we take 25 and divide it by 5, that equals 5, and it also equals 5 to the first. So if we take 5 and we divide it by 5 one more time, that equals 1. And if we subtract one of the 5's from here, we have 5 to the 0. Now if we continue and we take 1 divided by 5, we get, and we subtract the 1 from here, we get 5 to the negative 1. We continue, we have 1 over 5, and we divide it by another 5. That gives us 1 over 25, which is 5 to the negative 2. Okay, so that kind of gives you an idea of how these exponents are working. All right. So let's get back to the question, what is 3 1/2? So if we look at this, we have 3 1/2. If we square that, we can use the power of the power of a power, and we can square that. So then 1/2 times 2 over 1 is just 1. So 3 to the 1 is just 3. We can also do that using the product of powers. So if we take the product, which means multiply them, 3 and a 1 to the 1/2 times 3 to the 1/2, we can add the exponent. So 3 to the 1/2 plus 1/2 equals 1, which equals 3. Now this is how I think with what is 3 1/2. So now let's look at square roots. So 3 and the square root of 3 times the square root of 3. Now we don't normally write the index 2. I'm just writing it there for emphasis that this is a square root house. Okay, so, but I can take this 3 and multiply it by this 3. And we know that with a square root house, you can't leave home unless you leave in pairs. We have a pair of 3, so they get to leave the house as 3. So what that means is, since we have a 1-to-1 correspondence here where this times this equals 3, then this has to equal each other. So therefore, 3 1/2 has to equal the square root of 3. And this fancy little triangular 3 dots means therefore. So yes, therefore, I expect you to use cool lingo like that. Cool symbols to show how educated you are in math. All right. So this brings us to another big aha moment. Okay, so we have, if the nth root of a number a is a real number and m is an integer, that means -4, -3, -2, -1, 0, 1, 2, 3, 4, like as such, then I have a to the 1 over n equals n, the nth root of a. So we pronounce that the nth root of a. Okay. So if I have an exponent with the root, so if I have an exponent m with the root n, so I have a to the m divided by n, then that's the nth root of a to the m. Or I could write this in a different way. I could write the nth root of a with parentheses to the m. So there's a few ways to write that. So it all means the same thing. So let's get into some problems. All right. So we have, what does 2 and 1/3 equal? So we could use the power of powers and say 2 and 1/3, and then we could cube it. So that equals 2 to the 3 over 3, which we know 3 divided by 3 is just 1. So we have 2 to the first equals 2. So now we know if we cube this, we will get 2. We also know that if we take 2 to the 1/3 times 2 to the 1/3 times 2 to the 1/3, we can add these together and say 2 to the 1/3 plus 1/3 plus 1/3 equals 2 to the 3 over 3, which is 2 to the 1 is 2. Okay, so that's using the product of powers, where we add the exponents, as opposed to the power of powers, where we multiply the exponents. So then if we use the fact that this is supposed to be the root, let's check it out. So if we have the cube root of 2 times the cube root of 2 times the cube root of 2 should equal the cube root of 2 times 2 times 2. Well, we know the index says you can't leave the safe house. That neighborhood's getting pretty bad. You can't leave the safe house unless you leave within a group of 3. We have a group of 3, so this ends up being 2. And look, they all equal. So now we can look and compare, and we see we have a 1-to-1 correspondence here where that equals 2, this equals 2, and we're multiplying like that. So that means that the cube root of 2 has to equal 2 to the 1/3. All right, so now let's take a look at this. So we have the same base and 2 exponents, and it's a product of powers. So that means that we can rewrite this 2 to the x over 4 plus x over 6 equals 2 to the 3rd. So if we have the same base and we have exponents here that look different, these exponents logically have to be the same thing. So this has to equal that 3 for this 2 to the x plus 4 plus x plus 6 to equal 2 to the 3rd. So this has to equal 3. So instead of including the bases now, let's solve for x with that assumption. So what we're going to do is write just x over 4 plus x over 6 equals 3. Now we're going to use the ninja move of fraction busting, because we have an equal sign right here. So we can do that because we can multiply something on this side and multiply something on this side. So what we're going to do is we're going to multiply both sides by the least common denominator. So the least common denominator of 4 and 6 happens to be 12. So now we can rewrite this as 12x over 4 plus 12x over 6 equals, and 3 times 12 is 36. We know that there are 3 4s in 12 and 1 4 in 4, and there are 2 6s in 12 and 1 6 in 6. So now we can rewrite this without fractions, which makes it so much easier. So we have 3x plus 2x equals 36. So then this is 5x, because we can combine our like terms, equals 36. Now we need the 5 to go away, so x is alone. So it's multiplying x, so we're going to use a multiplicative inverse and divide using the opposite operation of multiplication is division. So we're going to divide by 5 on both sides. What that does is this becomes a 1, that becomes a 1. So now we just have x equals 36 divided by 5. So let's write that over here. So if we divide 36 by 5, we get 7 with 1/5 remaining. And 1/5 is the same thing as 7.2. So that would be our answer for what is x. All right, so we were fortunate enough to have the same base, but we don't always get problems that have the same base, so we have to kind of play a Where's Waldo game and find that base that's all the same. So on these problems, we're going to have to find that base. So I see I have a base 4 here and a base of 256. Well, that's just not going to work for us, is it? So what we need to do is take 256 and do we're not going to do a prime factor tree. We're going to factor it by the base 4 because we need to know how many 4s make up 256. So when we divide that by 4, 256 by 4, we get 64. When we divide 64 by 4, we get 16. When we divide 16 by 4, we get 4. So now we know 256 is 4 to the 4th. So now we can change 256 to 4 to the 4th. So we have 4 to the 4th with an exponent of x plus 2. Now this equals 4 to the 3x plus 9. All right, so we want to do we have a power of a power here, so we can multiply these two. I'm going to erase this now so I have some room. And fasten your seatbelts. So we have 4, and we're going to distribute this 4. We have 4, and I'll just write one step out here so I don't lose anybody. So that's what multiplying a power of a power is. And then we just have equals 4 to the 3x plus 9. So now that we have the same base and we have exponents, we can just take this and bring it down, and it's just an algebra problem from here on out. So we have 4x plus 2 equals 3x plus 9. So we use the SAM. We simplify by distributing. So we have 4x, and then 4 times 2 is 8 equals 3x plus 9. So now we're going to use an additive inverse. So that's the A of the SAM. So I'm going to use an additive inverse for 3x, which is negative 3x, and move that over here. Now I'm going to do 2 steps at once, so please fasten your seatbelts. I want this one over here. So I'm going to use the additive inverse of negative 8 to move that to this other side. So we don't have to do one additive inverse at a time. We can do 2 of them at a time. So 4x minus 3x is just 1x, or x, since we don't write the 1. We have plus 0 here equals, this is another 0. And then 9 minus 8 is just 1. So now we have x equals 1. And that's our answer. So we can put this back in here. Probably this one would be best. We can put 4 times 3, 1 plus 2 is 3, is 12. And 3 times 1 is 3, plus 9 is 12. So it works out perfectly. All right. So if you thought that was crazy, now let's do this. Okay. So we have to look at, well, what is 8? And 8, let's do a prime factorization tree. So we're going to take 2 out. We have 4. We have 2, and that's 2. So we find that 8 is 2 to the third. When we prime factorize 4, it's a lot easier. It's just 2 and 2. So 4 is 2 squared. So now let's put that into this problem, because we have the base of 2 that's the same, so we can work with that. So we have 1 over 2 cubed, and now we have this lovely exponent x over 2 minus 1 equals 1 over 2 squared, and then we have x over 3. I'm going to erase this for some room. So now I don't want this base in the denominator, I want it in the numerator. So I'm going to make it like an angry teenager. I'm going to put it where it doesn't want to be. And how do you feel when you're angry? Pretty negative. So now I'm going to take this and put it up in the numerator and make it a negative exponent. So x over 2 minus 1 equals, and then we have 2 to the negative 2, and then x over 3. So now I have again the power of powers. So this is all together here. So, and I have the same base. So now I have 2 to the negative 3 times x over 2 minus 1 equals 2 to the negative 2 times x over 3. Okay, so since I have the same base, I can make this an algebra problem now. So I don't need to write the bases. These exponents have to be the same for this to be equal. So I'm going to write negative 3 times x over 2 minus 1 has to equal negative 2. And let's multiply that one out because that's pretty simple. Negative 2x over 3. All right, so let's distribute the negative 3 to both terms. So negative 3 times x over 2 is negative 3x over 2. Negative 3 times negative 1 makes a positive 3 equals negative 2x over 3. So we have a 2 and a 3 in the denominator. We don't want to work with fractions. And we have an equal sign, so we can use a fraction buster. So we're going to take this whole thing. We note that the least common denominator of 2 and 3 is 6. So we're going to multiply that by 6 and this side by 6, because we can't just multiply it on one side, we have to do it on both sides. All right, so here we go. Mr. Toad's Wild Ride. Okay, so now we're going to distribute this 6 to this term. So we have 6, I'll write it here, so 6 times negative 3x over 2, and 6 times 3 is 18, equals, and now we're going to multiply the 6 here, so 6 times negative 2 is negative 12x over 3. All right, so we can reduce this fraction here by dividing it 2 by 2 and 6 by 3. So, and we can reduce this by dividing 12 by 3, making that a 1 and this a 4. So then we have 3 times negative 3 is negative 9x. And now no denominator, yay! Okay, now we have plus 18 here equals, and then this is just going to be negative 4x. So I have two things here. I want to move what's like this over there. So this is my like term, a variable term. This is my constant term. So I'm going to use an additive inverse and put a plus 9x here and a plus 9x here, because I have a balance bar going on. What I do on one side, I do on the other. So I have a 0 plus 18 equals, and then negative 4x plus 9x is 5x. So now I don't want, so I used an additive inverse here. I simplified. So I want to get the SAM process going on pretty well. We missed we only had saw right here. This one we're going to actually have the rest of it. So we simplified, we did an additive inverse. Now we're going to use a multiplicative inverse. The opposite of multiplication is division, and I want the x by itself. So I divide by 5. I don't need to divide 0 by 5 because that's just going to be 0. So let's just take that 0 away. So now I have the m of the SAM. See, simplify, additive inverse, multiplicative inverse. So if you ever forget what to do, remember SAM, simplify, additive inverse, and then when you're down to two things, that's when you use the multiplicative inverse. So when we simplify this, we have just x, and then x equals 18 over 5. Okay, so x equals 18 over 5. Let me put this over here. Okay, so there are 3 5s in 18, leaving 3 this left, so we have 3.6. So that is the answer for that. So that would be x. Okay, so these can be long problems depending on how difficult it is to isolate that base. Okay. All right, let's look at a real life problem. Probably like, why would we do this ever in real life? Well, here you go. Okay, so when the side of a square blanket is multiplied by 2 to the 1/2, the result is 6 yards. So we have this square blanket. So we know the square blanket has all the sides are equal. And so the area of a square blanket would be the length times width, or in this case, x times x, which is x squared. Okay, so we know that when we're only talking about the side of a square blanket is multiplied by 2 1/2. The result is 6 yards. So we're multiplying this by 2 to the 1/2, not 2 1/2, but 2 to the 1/2. X is going to be 6. So we have 2 to the 1/2 times x equals 6 yards. And we abbreviate yards like that. What is the original area and length of the blanket? Okay, well, we can find the new area very simply because we know that area is the side squared. So if this is equals the new side, and it's really hard to find x right now because we have 2 to the 1/2. So what we can do is area new would then equal 2 to the 1/2 x, and we're going to square that because we square the side, and then that's going to equal 6 yards squared. So we know that our area new then is going to be 36 yards, but when we square this, we're going to use the power of a product. So we're going to distribute this square to that. So we have 1/2 times 2, which is 2 over 1. And then also we have x squared. Now 6 squared equals 36. So 1/2 times 2 is just 1. So we have 2x squared equals 36. Okay, so we're about to find this area old, or A naught. Let's call it A naught. That's usually the original A naught. We pronounce that as not. I'm not sure the spelling, but it sounds like not. Okay, it's an English way of saying 0. So we have a 2 with our x squared. So this needs to go away. So what we're going to do, there we go. So what we're going to do is we have 2x squared. We're going to divide by 2 and divide by 2. So that's going to leave us an x squared equals 18. So now what I can do is I can take the square root of square, and I can take the square root of 18. Let me make a little room here. So I know that the original area now, I can say A naught equals 18 square yards. So that's the abbreviation for square yards, our English units. Okay. But now we need to find the length of the side. It asks, what is the original area? Well, that's it. And then what is the length of the blanket? So we're going to take the square root of the square. But when we do that, we had to add a plus or minus sign. The reason being, well, what if this was the square root of -3 squared? That just equals the square root of 9, which is 3. Or I could have the square root of +3 squared, which equals the square root of 9, which is 3. So there's nothing to rule out that I don't have two negatives being squared here. So when I find the length of that number, I have to put a plus or minus. However, we are finding the length of a side. this length here. Can this length be a negative number? No, length cannot be a negative number. So now I'm going to erase the minus sign because I've ruled that out, that there's no way that this can be a negative value. So when I have the square root of x squared, that's x times x. Okay, when I prime factorize 18, I have the square root. Let's do that. Let's do 18. Let's see. 18, if we do a prime factorization on 18, we take a 2 out, we have 9. We take a 3 out, we have 3. So I'm going to put the prime factors in here. All right. When I have 2 of a kind, they get to leave the safe house of the square root house. So that means this x gets to leave as a united front of x, and these 3's get to leave as a united front of 3. But this 2 is alone, so it stays home. So we have 3 square root 2 yards. So don't forget your units when you're working on real life problems or problems that have units, because units make a big difference. An inch is much different than a mile, or a meter is much different than a kilometer. Okay? So that would answer that question. I have one more example for you. We're going to look at a terrarium now. All right, so what is the value of x if the side length of terrarium A is 4 times the side length of terrarium B? So here's terrarium B. Now it's a cube. So each side is x to the x subscript B to signify that's the side of terrarium B. So the volume of terrarium B then equals 2 meters cubed. So that's not an m as in a variable, that's an m as in meters. Okay, but then we know that terrarium A has a volume of 2 to the x m cubed. So we have to find the value of x. That's what our mission is here. So we see that the side length of terrarium A is 4 times the side length of terrarium B. So we would multiply this to be the side length of terrarium A. Okay, but we also know that 4 can also be written as 2 squared xb. Okay, 4 is 2 to the second. So now we have a base 2 here and a base 2 on these volumes. All right, so volume, if you don't remember, is for a cube is length times width times height. So in this case, our length, width, and height are all the same. So that's where we got x to the b cubed. So this would be volume B. So we know that volume B happens to be 2 meters cubed. So now we can find x to the b, and when we find x to the b, we should be able to figure out what this exponent is on this volume for volume A. All right, so we see that we have a cube root here, and we don't have a cube root. We have an exponent of 3. So we do need a cube root to get rid of that exponent. So we're going to take this and do that. But since we're learning about fractions, let's use the fractional exponent. So if I have x to the b cubed and I take 1/3 of that, I'll get x to the 1. And then if I take, that's going to equal 2 to the 1/3. Let's make that 2 meters cubed. So you can see how the units work. To the 1/3. Okay, so if I have x b to the 3/3 equals, now I'm going to distribute this. So I have 2 to the 1/3, and I have meters cubed over 3, because this is a unit, not a variable. But remember, we're looking for a length of a side. So now we have x to the b equals 2 to the 1/3 meters, which makes sense because this should be in meters, this should be in meters, this should be meters. So volume, which is a length times width times height, I have meters times meters times meters, which is meters cubed. So each one of these should just be meters. So when we did that, we see, yes, it is. So now let's find this x here. All right, let me clear out another board. So we want to find volume A. So we have volume A equals 2 to the x meters cubed. We know that the side of A is xa to the cube. We also have set this up that x to the a cubed equals 2 squared x to the b if we use substitution. Okay, so now we have that side x to the a, but we're going to cube this. But wait, we also know x to the b, so we can substitute x to the b in here and then cube it. So we have volume A equals 2 to the x meters cubed, and this is in meters. Right here, I'm going to put meters there. So meters cubed equals, and we don't really need this, and we're going to substitute that in here. So this is going right there. So now we have 2 squared times 2 to the 1/3, and then we're going to, and we've got meters in there, because that's just one side, and now we're going to cube it. Okay, so now we're going to use the power of a product and distribute this to each one of these. So we have volume A equals 2 to the x meters cubed equals, and then 2 times 3, so I have 2 times 3 times 2 and 1/3 times 3 times the meters cubed. Okay, I'm going to put this other board back so we don't miss anything. So we have volume A. I think we can divide both sides by meters cubed. Okay, because we're just trying to find x, so we don't need that, and it gets a little confusing. So if you do it to one side of the equal sign, you can do it to the other. So now we just have 2x equals 2 to the 6 times, and 1/3 times 3 is just 2 to the 3/3, which is 1. So they're all the same base, so now we just do algebra. X equals, well, let's do one more line. So I have 2 to the x Oh, this is not appropriate right now. Oh, actually, it still is. Okay, volume A. So 2 to the x equals 2 to the 6 plus 1. So that gives us, now we can set these equal because the bases are equal. So we have x equals 6 plus 1, which is just 7. So our exponent x is 7. So our original formula right here, this one right here, this x is a 7 for an exponent. So that's what we just found with all that hard work. All right, so we have VA equals 2 to the 7th meters cubed. All right, that's it for rational exponents and properties of exponents. I hope you're doing well and have a wonderful day. Bye-bye.